All right, so I want to go over the procedures for hypothesis testing in general, and then we're going to try 3 of them tonight. All right, so let me share the screen and go to the textbook. All right. All right, so we'll do the proportion one first. And when we do any hypothesis test, the first thing we have to formulate is the null and alternative hypotheses. The null hypothesis, now I'm going to tell you something different than what's here. I want you to always use an equal sign in the null hypothesis. It's just unnecessary for you to use greater than or equal to or less than or equal to. Some students get confused with that. So we'll just use an equal sign. And then for the alternative hypothesis, we're going to use greater than, less than, or not equal to. We're going to use HA instead of H1. Okay. Now, so step number 1 is to have our null and alternative hypothesis. That's the first step. And then step number 2, doesn't mention it here, but we have to establish that we can use an approximately normal distribution for our sampling distribution. So we're going to use the same procedure that we used in confidence intervals. If the hypothesis test is for a mean, we're going to check to see if the sample size is at least 30, right? Unless, of course, the population is normal. Population is normal, doesn't matter. But if there's no information about the population, sample size is at least 30. And for a proportion, we have those 2 criteria. It says it right here. N times the population proportion and N times 1 minus the population proportion. They both should be at least 5. Right? All right. We talked about that last time. Mm-hmm. So that's really step 2 when you do a hypothesis test, because otherwise you can't do it. You don't meet the normal distribution requirement for the sampling distribution. Everything that we learn here is a waste of time. Right? It all depends on bell-shaped curve. We probably would have to go to a StatKey and do a randomization, one of those randomized hypothesis tests. All right. Now, and also, of course, we have our 1-tail test, 2-tail tests. That depends on the alternative hypothesis. The alternative hypothesis has less than symbol in it. It's a left tail test. Greater than symbol, right tail test. Not equal to symbol, 2-tail test. All right. Han, you're good with that?
You can repeat that?
Left tail test mean that we would go with a left tail test when the alternative hypothesis is less than. Mm-hmm. Right tail test for greater than. 2-tail test for not equal to.
Okay.
Now, the third step is to calculate what's called the test statistic. Now, for proportion, it's basically the z-score. All right, always for proportion, z-score. Now, remember, we're modifying the symbols a little bit here. We're saying that P is going to be our population proportion, and P hat, the little hat above it, is going to be our sample proportion. So this should read P hat minus P divided by sigma P hat. All right, but I think you get the idea, right? Yeah, it's just basically it's the sample statistic minus the hypothesized value divided by the sampling distribution's standard error. All right. Now the standard error for a, again, you don't get confused with the symbols. The standard error for a hypothesis test for a proportion, the square root has within it the population proportion times 1 minus the population. It's different than in a confidence interval. Remember, confidence interval, we don't know the population proportion. So instead we use the sample proportion. But we do have a hypothesized value in the null hypothesis when we say it's equal to some number. And that proportion we're going to stick right into the formula. All right? Make sense? We always prefer putting in the population proportion in the formula. All right. I'm assuming that no response means you understand. Two-tail testing of report proportion, of course, requires us to use two tails instead of one tail, but we'll get to that in a second. Now, once we calculated our Z statistic, our test statistic, what we're going to do, the traditional way of doing this in real research, not the method that they show here, is the p-value method. The p-value method. Here they're just basically putting in the alpha, your probability of a type 1 error. They're putting the alpha in, well, if it's a two-tail test, they're dividing the alpha by 2 and putting them in each of the tails, and then we find the critical values. And then we plot the Z statistics somewhere along here. If it's in this region, we don't reject. If it's in the yellow regions, we do reject. But a better method is the p-value method. I think I showed you that last time, right? We were doing some simulations, right? In Stacky, I believe. So instead of putting in the alpha in here, what you're going to do is you're going to plot the actual sample statistic on the graph. All right, you're going to plot it. Now, for a two-tail test, it's either going to be positive or negative for the Z, right? Because the middle is 0. It's going to be over here or over here. Doesn't really matter. And then what you're going to do is you're going to find if you're plotting on the left, the area to the left of that sample statistic is the p-value. Excuse me, it's 1/2 the p-value in a two-tailed test. Because you have the other side here also. All right. This side and this side are going to be equal to each other. So you plot your sample statistic, and then the area that you're finding is the p-value. So you have to make sure that you add the two tails in a two-tailed test, right? And that's it. That's how you figure out what's called the p-value. You just plot the sample statistic, which is what? It's the, or the test statistic. It's the Z that you calculated up here. You just plot it and find the area. All right. You have any questions about that? All right. Now, for a right tail test and left tail test, you're going to find the area you find is it's the entire p-value. So for a left tail test, the area to the left is the p-value. The area to the left of the test statistic. For a right tail test, the area to the right is going to be the p-value, the full p-value. And then this next step is you're going to compare the p-value to alpha. I think we went over this last time. When the p-value is less than or equal to alpha, the level of significance, then we reject the null hypothesis. When the p-value is greater than alpha, we do. And the reasoning, just if you can remember the reasoning, you'll never question the decision rule. The reasoning is that you are willing to reject the null hypothesis as a researcher up to a certain probability for the type 1 error. In other words, if you reject the null hypothesis, there's a chance you're going to make a mistake, right? The null hypothesis is actually true. So you as a researcher, you're coming up with your alpha ahead of time. That's your decision ahead of time, is to do that. And what you're basically saying when you choose that alpha is that's the maximum type 1 error I'm willing to tolerate. All right? Does that make sense? Okay. So if you calculate your p-value. Now, your p-value, you can actually state, it's not wrong to say it this way, it's the actual p-value that you're getting, all right? It's the actual p-value from the sample that you have. So the alpha is your theoretical p-value. It's your upper limit to what you're willing to accept as a type 1 error. The actual p-value that you're getting is your, excuse me, the actual type 1 error is your p-value. Because the p-value is defined as the probability of getting that sample statistic or something more extreme than that. And that's exactly what a type 1 error would be. Because you're assuming what? You're assuming the null hypothesis is true. So you're rejecting the null and you're assuming the null hypothesis is true. So that's what a p-value is. So if a p-value is less than or equal to alpha, and you're already saying, I'll accept for an alpha of 5% or less as a type 1 error, you get a p-value less than that, that's part of the definition, isn't it? You're okay with that. That's why you're saying, okay, I'm going to go ahead and reject the null hypothesis because my p-value is low enough, it's below my alpha, that I'm okay with that. I'm okay with that type 1 error. But if your p-value is bigger than your alpha, that means you're not going to be able to, you're not going to take that chance and reject the null hypothesis because it's bigger than that limit of alpha, the type 1 error. All right. If your p-value is 10% and your alpha is 5%, there's no way you're going to reject the null hypothesis because you're saying the probability of a type 1 error, the limit is going to be 5%. If it's more than that, I'm not going to take the chance and take that chance. All right. I'm not going to take the chance and reject the null hypothesis and make that mistake. So do you get the idea? So you want your p-value to be less than or equal to alpha because that's what you've come up. That's your decision. That's what your decision should be. Now, the reason why we do it that way instead of the way they show it in the book here, this is legitimate. Actually, it's the same exact thing, to be honest with you. You're plotting the alpha, and then you're also plotting your test statistic and seeing if it's in the rejection regions. It's exactly the same thing. There's no difference. Because if you plot alpha, if you plot your test statistics and it's over here, well, your p-value is going to be to the right of it. And it's less than or equal to the area of alpha here. You see what I'm saying? So it's exactly the same thing. The only reason I teach the p-value method is because that is what researchers use. That's what they use when they publish papers. They use p-values. Almost every researcher, any research article you'll ever read where they're doing research and they're publishing something like something like this, they're going to tell you what the p-value was. All right, they're going to just state what it is, and they want that p-value to be as small as possible. If it's better, it's close to 0, and therefore it doesn't even matter what alpha is. If it's close to 0, it's highly significant. That's the way that researchers talk. All right, you get the idea of the general idea of what to do. So, and once you have, this is very important, once you have your decision,
I think so.
then you always state, I'm sorry, Steve, you said something? All right. Once you have your decision.
No, sorry, there must have been a delay. I just said, I believe I understand.
All right. Once you make your decision, the very last step, which is the 6th step, if you counted all those steps, the 6th step would be interpretation. And you always start off the interpretation with at the blank % level of significance. All right. Because what if your p-value is 0.04, right? Well, if your alpha is 0.05, then you reject the null hypothesis. But if your alpha is 0.01 and your p-value is 0.04, you do not reject the null hypothesis. So sometimes in those intermediate cases, this is why a lot of people think p-values are ridiculous, but because you have this cutoff, right? Your alpha is your cutoff. So alpha determines whether you reject or don't reject. So that's why in your interpretation, you always have to say the level of significance first. You say at the 1% level of significance, there's enough evidence to reject whatever the claim is, all right? Or you could say at the 5% level of significance, there's not enough evidence to reject the claim. All right, you get the idea? So you always have to state the level of significance in the hypothesis test because it could change your decision, which one you choose. And that's why it would be very unethical for a researcher to not state their, or not to decide their alpha up front and just look at, and then look at the data and then come up with their alpha so that they can reject the null hypothesis, right? Because that's what they want to do. That would be unethical to do that. All right, so now you know the general rule. Now, there's a couple things I want you to try on your own tonight. And I don't expect these 3 problems for you to get all of them correct on the first try. All right, this is just a first try because I'm going to give you more problems as homework to do. But these 3 problems will be guides for you. So now, one other thing I do want to describe to you is the other 2 hypothesis tests. And that is testing a mean if the population standard deviation is known. All right, there we go. And it's the same 6 steps. The difference here is if we know the population standard deviation, then we calculate a z statistic. And this time the numerator is going to be x bar minus the hypothesized mean divided by the standard error. And the standard error is the population standard deviation divided by the square root of n, right? You already know this. We did this with confidence intervals, right? We know the standard error and we know the population standard deviation. Now, what if you don't know sigma? All right, what if you don't know sigma? Let's go to this section here. So the population standard deviation is unknown. Then we replace sigma with the sample, with the sample error. The standard error now is going to be using the sample standard deviation. It's from the one sample that you have divided by the square root of n. That is your standard error now. And the numerator is exactly the same. But this whole statistic now is called a t. This is actually the definition of a t, right? Where the numerator is x bar minus the mu, and the denominator is the standard error. But the standard error is in terms of the sample standard deviation, not the population standard deviation. So when you calculate your t statistic, and when you find your areas, your p-values, this is very important. You're going to be using the t distribution, not the normal distribution. All right? Because it's a t now, it's not a, all right? So that's the difference. You're going to use the t distribution if you're going to use Excel, not the normal. All right? Everything else is the same. Exactly the same 6 steps. Okay, does that make sense? All right, because this is not a z, it's a t, this definition here. All right, so what are we going to do now? I'm going to give you the problems, and again, I'm going to give you let me see how much time we have. I think we've give you 10 minutes, maybe for problem number 1. You're not going to get through it, but I'll give you 10 minutes to give it a shot. And this first problem is on page 344. 344, where we're looking at proportions. This is a proportion problem. And it's number 60. 10.68. Let's just find it here. Read through it. Make sure you have Excel ready to go. All right. I want you to give it a try. All right, here's what it says. It says Heritage Union has said that 66% of US adults have purchased life insurance. Suppose that for a random sample of 50 adults from a given US city, a researcher finds that only 56% of them have purchased life insurance. At the 0.05 level, all right, now when they say 0.05 level, they mean 5% significance level, all right? In a one-tail test, they're actually giving you the tail test. Is this sample finding significantly lower than the 66% reported by Heritage Union, all right? So you have to decide whether this is a left tail test or a right tail test. Determine and interpret the p-value for the test. So what I want you to do is go through those 6 steps. I want you to do the null and alternative hypothesis first, write it out. I want you to determine from the data that's here whether you can do a normal distribution. All right, do that NP time and also N times 1 minus P. Step 3 is the test statistic. Step 4 is your p-value. Step 5. Step 5 is going to be your decision, comparing it to alpha, p-value compared to alpha. And step 6 is an interpretation. Now, I don't expect you to get through all of that in 10 minutes. On a test, I do. When you're ready to take a test on all this, you better get it done in 3 minutes or 4 minutes. At least have a sketch of how to do it. All right, so go ahead and work on that. It's about 11 minutes after, so about 21 minutes after. I'll ask you to stop, and then we'll go over it together. All right, so just do the best that you can. The symbol that we want to use is P for the population proportion and P with a little hat above it for the sample proportion, not what the book uses. Okay? All right, go ahead and back in a minute. Guys doing okay?
So far.
Okay. All right, just one more minute, and then 'cause we have two more to do. So Steve, did you finish?
Yeah.
Okay. All right. How about you, Han? Are you done?
Halfway.
Halfway. All right.
Whether my answer is right, by the way, is up for debate.
Oh, all right. That's okay. All right. So I'm going to share um, the solution page here. All right.
Sir?
So hopefully you got part A, right? Part A is a left tail test. Yes, so that looks good. P is equal to 0.66, obviously will be the null. That was given as the population portion, and P is less than 0.66 is your alternative hypothesis. Han, did you get that? Yes? Han, did you get it? Okay. All right, good. Now remember, I'm using P hat. This is the P hat here is the sample proportion, because this is the typical, this is the more typical notation you'll see in real life, not what the book shows here. It wouldn't surprise me if they rewrote this book, they would show this notation instead of the pi thing. Now, part B is the determination of whether we can use the normal approximation for the sampling distribution. And the answer is yes. Because when I multiply, now you need to multiply 50 times 0.66. This is the hypothesized proportion, and not the 0.56. So, because remember, you do all of this stuff, parts A and B you do before you've actually even acquired a sample. All right. You're going to determine whether your sample size is going to be big enough, and you want to make sure that n times p and n times 1 minus p is greater than 5. So you understand what I'm saying? You have to do this before, so you don't use your sample proportion. This is not even known at that point in time. All right, part C is your test statistic. So we're going to use p hat minus p sub 0 in the numerator. And the denominator, remember using p sub 0, the 0.66, use that inside here, not the 0.56. All right, so this is your test statistic. I get negative 1.4927. Both of you got that? Okay.
Yes.
Then we're going to plot that on the z-axis, where 0 is the mean. And of course, it's negative, so it's going to be on the left. And when we use our normal probability, we should get a p-value of 0.0678. You get that? Yes? Han, did you get it, or you weren't there yet?
No. Can you explain that a bit?
You got it, Steve. Okay.
Yes.
So in Excel, you would just find the area to the left. So you would use normal dot dist.
Oh,
Yeah.
okay.
You're finding the area. That's what you're doing. All right. And remember the normal distribution functions is asking for the area to the left, and that's what you have here is the area to the left.
Oh, okay. Okay.
Right? Yeah. So that's your p-value. Now your alpha originally was what? What was the alpha? What was given as a problem?
0.05.
Right. So this is bigger than alpha. So your decision in E is to not reject the null hypothesis. And then you would write up something like, at the 5% significance level, there is not enough evidence to reject that 66% of US adults have purchased life insurance. Another way of saying it is there's not enough evidence to support the competing claim that less than 66% of US adults purchase life insurance. All right, you'd say both. Now, what I want you to do, it's a harder question, but it's an additional question I'm going to ask you to do. I'll only ask you to work on it for a minute. If you don't know how to do it, we'll just look at the solution. All right. Suppose that we happen to find out through some crystal ball or something that the true proportion, the true percentage, the actual percentage in the population is 61%. In other words, it is a number less than 66%. It's 61%. What is the probability of a type 2 error? What is the probability of the type 2 error, given that the real probability is less than 0.66, and we know it to be 0.61, or proportion, not probability. What is the probability of a type 2 error? You do have to think about this for a minute, but if you don't have any idea, that's fine. We went over this before, how to do something like this, but
How long do we have to solve it?
1 minute. If you can't figure it out, well, you have an idea of how to do it? I'll give you an extra minute if you think you know how to do it.
I need a minute to think about it.
Okay. All right. You think you can do it, or should I just go ahead and show you?
This is a pretty uneducated guess, but my guess would be that the probability of rejecting the null hypothesis when the null hypothesis is false would be 5%.
Okay. Good try.
Okay, yeah, let's see the answer, please.
All right, well, let me define what a type 2 error is again. The type 2 error is the probability of not rejecting the null hypothesis when the null hypothesis is false. Now, this is an appropriate question when you have come up with what? With a decision of not rejecting the null hypothesis, correct?
Mhm.
That's your decision. So it's appropriate to ask the probability of you making that a mistake. With this sample, you have made a mistake. Now, you didn't make a mistake in terms of the calculation. You came up with the correct decision, but it still could be a mistake because it's possible that you did not reject the null hypothesis and it's actually false.
Mhm.
So in the case that I'm giving you, I'm picking a particular falsehood. All right. The falsehood is that the population proportion is actually 61%, not 66%. So I'm giving you that specific number. So what you have to do is basically do the following. All right. Let's just scroll down. This is part G in the handout. All right. Wait a minute. I'm looking at the wrong problem here. Sorry. All right, here we go. All right. What you have to do is you have to recalculate your test statistic. Based on what?
Mhm.
Based on 0.61 now, not 0.66. This is your new population mean. This is a fact now. It's not even a guess anymore. It's a fact. All right. Now your denominator, you have to be careful because now you need to put 0.61 in for your population proportion instead of 0.66. Anyway, when you do this new test statistic, you come up with negative 0.7249. So here is the, now I hope you get what I'm saying with that part so far, right? New test statistic. All right. It's the same sample statistic, by the way. That hasn't changed. It's 0.56, right? But the mean, excuse me, the population proportion is now known to be 0.61. We're going to use it. Now, remember, a type 2 error is we do not reject the null hypothesis. We do not reject it, right? When it's known to be false. Well, 0.61 is, right? Null hypothesis is false here, right? It was originally 0.66 and now it's 0.61. It's false. However, it's asking for the probability of not rejecting the null hypothesis. So let's think about that for a minute. Let's go back to this was a left tail test, right? The probability of rejecting the original null was the left tail.
Mhm.
The probability of not rejecting it would be the right tail, right? Not rejecting, knowing this to be true. So obviously the probability of not rejecting has to be to the right in this case because it's a left tail test, right? Would you agree with that? Yes.
Yes.
So therefore, you should take your test statistic and find the probability that Z is greater than that, greater than or equal to that. And that is going to be your beta. That's going to be the probability of type 1 error. The probability of type 1 error is specifically with reference to this 61%. If we basically it's saying if we know the actual population proportion is 61%, the probability of a type 2 error is the probability that Z is greater than this test statistic. And that's 0.7657. So this is a very high type 2 error here. All right, it's high, right? It's large. But it makes sense it would be large, right? Because of what? Why is it so large? It's because 0.61 is closer to 0.56 than 0.66 was. All right. 0.56 is closer to 0.61 than to 0.66. So we expect pretty large type 2 error. And by the way, the probability, and it doesn't apply in this case, but if we want to know the power of the test, it's 1 minus beta. 1 minus is the power of the test. But this is how you would figure it out, because it's based on logic. The type 2 error is the probability of not rejecting, right? The type 2 is the probability of not rejecting the null hypothesis. Right? So that means it's the area to the right, not the area to the left. That's the key to understanding this. If we were interested in the power of the test, then the answer would be area to the left of this test statistic. So that's beta. Steve, does that sound all right? Han, you were nodding. I think you kind of got it, right? Yeah. Makes sense?
Yeah,
I want to make
think
sure
so,
it's
yeah.
makes sense logically, that this is the answer for this. Now, this wasn't part of the problem. I'm adding it to it because I want you to understand that because your decision was to not reject the null hypothesis, you could have made a type 2 error here. And therefore, I'm asking you, what's the probability of that error that you could have made? Now, obviously, if I ask you a question and you come to a decision of rejecting the null hypothesis, then what's the you know what the type 1 error is, right? Already, it's alpha, right? You know the type 1 error is alpha. But I could ask you, what's the power of the test, right? What's the power of the test?
Mm-hmm.
The type 1 error, you already know, 0.05 or 0.0, whatever it's given in the problem, that's the answer. That would be an easy question if I ask you that question, right? Reject the null hypothesis, what's the probability that you made an error? And the answer would be already given in the problem. It would be alpha. I think that's what you were probably thinking about, Steve, before when you answered alpha.
Yeah. I was thinking about how that might change, but yeah, it's not the right way to think about it.
Right. Okay. So let's go ahead and let me just hold on 1 second here. Okay. All right, let's look at problem 93. This one is on page. I'll give you 10 minutes. Let's make it less than 10 minutes. 10 minutes is too long. Let's make it 7 minutes this time. This is on page 357. This has to do with a sample mean question. It's number 93. So let me look at it. Let's go back to the book. That's actually towards the end of the chapter, during the chapter review. All right, so it's number 93. Before the hiring of an efficiency expert, the mean productivity of a firm's employees was 45.4 units per hour. All right, so this is before a sample was done, with a standard deviation of 4.5 units per hour. This is a population standard deviation. All right, it's implied by the problem here. After incorporating the changes recommended by the expert, it was found that a sample of 30 workers produced a mean of 47.5 units per hour. Using the 0.01 or 1% level of significance, can we conclude that the mean productivity has increased? All right, what kind of test is this? Is left tail, right tail? Which one, what kind of test?
Right tailed.
That's right. So go ahead and work on it. Shouldn't take you very long now. That's why I'm giving you 7 minutes. The third problem, I'm only going to give you like 4 minutes. So go ahead and do it. You know the steps now. Yeah, work through them. And quarter to 8. All right, we'll talk. All right, I think you guys are just about done, right? Okay, let me pull up the solution page. All right, so the null and alternative hypothesis is these two statements here. Mu is equal to 45.4 for the null and greater than 45.4 for the alternative. N is 30, of course, which makes it large enough to assume a normal distribution. Part B. Part C, since we know sigma, we're going to use a z statistic in this case. And it's going to be x bar, which is the sample mean is 47.5. The hypothesized mean is 45.4. We subtract those two, divide by the standard error, which is the standard deviation of the population divided by the square root of the sample size. You get about 2.556 for the test statistic. Is that what you got?
Yes.
Okay. Now this is a right tail test. So we plot the 2.556 on the z standard normal curve. The area to the right of it, I get 0.0053. Is that what you got? Something like that?
Yeah. 5294. That's what I got.
Okay. And then since alpha is 0.01, and this p-value is less than alpha, we're going to reject the null. And therefore, we're going to say something like this: at the 1% significance level, there is enough evidence to reject the mean productivity of 45.4 units per hour and support the claim that it's larger than 45.4 units per hour. I should have said units per hour. All right, so that's it. Now, the bonus question is, what if the true mean is 49, not 45.4? What if the true mean is 49 units per hour? Okay, something bigger than 45.4, 49 units per hour. What is the power of the test? Take a minute, see if you can think about how to at least set it up. I'll show you the answer in about a minute. Are you, you sort of know what to do? Or not really?
I got an answer, but I don't know.
All right.
I don't know.
Well,
Right.
well, what's your answer, Steve?
The answer I got was 0.966.
Very good. That's correct. So remember, in this case here, the power of the test is, you are rejecting the null hypothesis, right? You're rejecting, right? The power of the test is you're rejecting the null when the null hypothesis is false, all right?
Mm-hmm.
So the direction of the symbol in the probability statement for the power of the test is going to be in the same direction as the original alternative hypothesis. So again, you just plug in 49 instead of whatever it was before, 45.4. Plug in 49 for your population mean. The denominator stays the same, by the way. You're assuming that the standard error is the same. All right, there's no change in that. That's the assumption. Now, in the case of the proportion, it does change, right? The standard error changes in the proportion problem, but it doesn't change here. All right. Okay. So when we calculate the z, we get negative 1.8257. And then we want to find the probability that z is greater than that. And that's 0.966. You're correct. On, how did you do with that one?
I have
Not
a question.
Yeah, go ahead.
Is it still a right skewed question? Like we still detect that we still need to find the I mean, how can we tell if it's right tail or left tail?
Because the question I'm asking is assuming that we're rejecting the null, that we're supporting the alternative hypothesis. All right. We rejected the null. We're supporting the alternative. The power of the test is stating that we made the correct decision. That's all. So it's the same direction. If the alternative hypothesis says greater than, then it's greater than also for the power of the test. Because in both cases, we're saying, both cases we're rejecting the null. We're supporting the alternative. Okay. So that's the general rule, I believe. Hopefully I'm not, now I'm pretty sure it's correct, that for the power of the test, if we're rejecting, if we're calculating the power of the test, we're interested in the same direction in the inequality as the alternative hypothesis. If we're calculating the probability of a type 2 error, we're not rejecting the null, therefore the direction would be the other way, would be the opposite direction. Right?
Oh, okay.
You see what I'm saying? So that's the way you sort of have to, you work it out that way. All right, the last question is 95 on the same page. And I'll give you now 4 minutes to get this done. So we'll talk in 4 minutes and then we'll go over it. And now you may not know how to do part B, but try at least part A as far as you can go in 4 minutes, and then we'll go over. All right. So
this is 10.95.
Yes, 95. So read through it. You both have the copy of the book? On, you have it there?
Yes.
All right. And Steve,
Yes.
you both see it. So go ahead and read it, and then instead of me reading through it, and then determine how to do it. All right. And again, in about 4 minutes, I'll read again. All right, guys, I know it's, it's getting late. I just don't want to, I want to go through the problem with you, but did you get at least some of it done? Okay,
Yes.
all right, good. Let's take a look at the solution. All right. So the problem, this is a different problem with means because we're not given the population standard deviation in this problem. We're given the sample standard deviation, right? These are home prices or something, I believe. Yeah. So they give us the sample mean, the size of the sample, 30, the sample standard deviation, and they told you basically to choose any alpha. I'm choosing 0.02 for the fun of it. All right. They did say it was a what is it? A non-directional test. That means a two-tail test. That's another way of saying two-tail. All right. The directional tests are either left tail or right tail. So this means non-directional means you don't really have the researcher doesn't have a preference for greater than or equal or less than. They're just going to say not equal to. So this is a two-tail test. I don't know if that's what you had seen. 30, of course, is large enough to assume a normal distribution for the sampling distribution. By the way, in addition to that, one of the requirements for doing a hypothesis test is that it was a random sample. All right, so random sample is important also. 3, since sigma is unknown, the test statistic is the t-score or t-statistic that we're going to use. We're going to use this formula up here. And the numerators, it looks exactly the same as the z-statistic. It's just the sample mean minus the hypothesized mean. And then the denominator is our standard error using the sample standard deviation instead of the population standard deviation. So I got 2.1909 for the test statistic. Now, this being a two-tail test, you will plot 2.1909 on the t. Now, this is a t distribution thing here, not a z. You have to be careful. And just know that because it's a t-test, excuse me, a two-tail test, you have negative 2.1909 on the left. All right. So you have the opposite on the other side. So this is just going to be whatever we calculate for this area here is going to be 1/2 the p-value, which I came up with 1.018322. You multiply that by 2, which is the sum of these two areas, you get 0.0366 as your p-value. I don't know if you got that. So that's good. If you got that, you remember to take your area calculation and multiply it by 2 because it's a two-tailed test. Now that's important. I picked alpha equal to 0.02 for a purpose, for a reason. Because if you forgot to multiply by 2, your decision is to reject the null hypothesis. But if you if you multiply this area by 2, then you're not going to reject the null hypothesis because the p-value is bigger than alpha. All right. So our decision is not to reject the null. And then the decision is at the 2% level of significance, there's not enough evidence to support the claim that the average household has $235,600 in life insurance. All right. I think that's not correct the way I said that. There's not enough evidence to support the claim that the average household does not have $235,600. So this is not stated correctly. All right. All right. Right. I mean, I said it incorrectly here. I'll have to redo this. Another way of saying this is there's not enough evidence to reject. I should have said to reject the claim that the average household has $235,600 in life insurance. So this is wrong. I should say reject. There's not enough evidence to reject. All right. So I will wipe that out and repost it. Don't print this out yet. I don't even think I've posted it yet anyway. So. Now, part B, just want to mention this to you quickly. For a two-tailed test, there is an equivalent confidence interval related to it. All right. The confidence interval, remember, is the sample mean plus or minus the margin of error. All right. Everybody, you're clear on that, right? Now remember, this is a t situation, so the critical value that we would choose for the margin of error would be one that in which the area to the right is 1%, right? Because confidence interval is 98%. That means the left tail is 1% and the right tail is 1%. So the critical value, the probability that t is greater than that critical value is 1%. And if you do an inverse t in an Excel using the area to the left is 0.99, because it's the middle, 0.98 plus the left tail, 0.01. With 29 degrees of freedom, you have to remember to use 29 degrees of freedom because it's sample size minus 1, you get a critical value of 2.462. Multiply that by S, the sample standard deviation divided by the square root of 30, you get approximately $11,462 as our margin of error. You just round it. And then if you add and subtract that from the sample mean, 245,800, you'll get your confidence interval. Now here's the big deal about confidence intervals. If we are relating it to a two-sided hypothesis test. If the null hypothesized value, which in this case was what? What was the null hypothesized value? 235,600. If that number, if that hypothesized value is inside the confidence interval, which it is, then that is equivalent to saying, do not reject the null hypothesis. Because this is normal variation. The whole idea of a confidence interval is normal variation around the mean, right? The population mean, right? The population mean is somewhere in here, and it's just normal variation around the population mean that we're talking about here. A 98%, or 98% sure that the true population mean is inside this interval. All right. So what I'm saying basically is, if you do a two-sided hypothesis test and you find, and you do not reject the null hypothesis, and then create a confidence interval that estimates that true population mean, and you find that the hypothesized mean in the hypothesis test is inside that interval, that's equivalent to saying, do not reject the null hypothesis. If we had rejected the null hypothesis, and then we created our confidence interval around the sample mean, then the hypothesized value would have been outside that interval, would not have been inside the interval. All right, so that's the relationship between a hypothesis test and confidence interval. And it is mentioned in the book. I'll just show it to you in the book, just quickly, show you what chapter or what section it's in. This section here where it says confidence intervals and hypothesis testing, page 329 and 330 in the textbook, is when they do they relate a two-sided test to a confidence interval. All right, so that's what we just did, this problem. All right, so you get the idea? If you create your confidence interval,
Yes.
and the hypothesis values in the confidence interval, that means you do not reject the null hypothesis. If it's outside the interval, you do reject it. All right, so that's a nice little relationship that it's good to know about. All right, so what I'm going to do is I will post in the next couple days or so. If it's not tomorrow, probably by Saturday, some homework for you to do. Probably I'll make it due on next Thursday. All right, so you have some time to get it done. All right, and the homework will include chapter 8 and chapter 9 and chapter 10, both confidence intervals, and also because I don't think I gave you homework on confidence intervals yet. So confidence intervals and hypothesis test give you homework for both. Maybe I'll count it as double. Count it as 2 quizzes, 2 homeworks instead of 1. All right. Maybe that's what I'll do. I'll make it 2 separate homeworks. Maybe 3, 4, 5, maybe 3 or 4 questions each. And then we'll start working on chapter 11. I think I've decided that I should give you some exposures to chapter 11 also. All right. We'll do that next week. Okay. And then the week after that will be on regression. All right. Introduction to regression. But not too much, just an introduction, enough of an introduction to get to make you want to learn more. Okay, so that's it for tonight. Any questions? Are we good?
No questions.
No questions. All right, so I'll put, once I make that little correction for this last problem here, the interpretation part I need to correct, I will post that, probably do it tomorrow. And then look out for the homework later on during the weekend. It will be due on Thursday. All right. And if you don't, if you decide not to do the homework over the weekend, that's fine. I'll just post it on and then give you until Thursday to get it done. And then of course I do want to give you, there's one more test, maybe 1 or 2 more quizzes. We don't have much time to do all that. And then you have your final also. So a little bit of testing here at the end. That's the way these courses are. There's a little bit of a crunch at the end. All right, but I'll space it out so you can there's time to get it all done. All right, any questions? Are you good? Lon, any questions? You're good?
No questions.
No? Okay. We never met, Han, right? We never met to go over the homework. We will. So when are you available next week for the homework?
Anytime actually.
Anytime?
I can work out a time.
All right. So maybe we'll pick a time. Let me think. Maybe next Tuesday.
Okay.
I'll send you email. Are you available morning or afternoon?
Doesn't matter.
Doesn't matter? Okay. So I'll pick a time and I'll send it to you over the
Okay.
week. All right. And Steve, are you okay? Do you need anything like that?
Not at this moment, no.
All right. Okay. Maybe in the future when it's too late. All right. All right. All right. So anyway, I'll see you guys later. All right.
Okay, see you later.
Yeah. See you later. Bye-bye. Bye.